Right, so chaps, we're going to continue this question now, which we were doing earlier. It is to do the big form of this little mini integral we were doing here. We're going to call this big form J. Because we called the last one I, yeah, kind of makes sense. J is integral from P to Q, which are about to be defined, of x minus a over b minus x to the square root of the x, where p equals 3a plus b over 4 and q equals a plus b over 2. Lovely. So, and b greater than a. That's relatively unimportant. Right, how to tackle this? Well, we're probably going to have to do a substitution, because that's what we did in the first part. Moreover, in the first part, we did a substitution of the form x equals a minus b cos theta, okay? Where a was 1 and b was 2. But what I want to say is, the limits, p and q, are probably going to change, or at least we want them to change, to the same things 1 and 1.5 and 2 changed to the last time. In other words, we'd quite like a and b to be chosen by us such that p transforms to pi over 3 and q transforms to pi over 2. With that in mind, we can write we want p to equal a minus b cos pi over 3 and q equals a minus b cos pi over 2. So let's use this to try and find suitable a and b for that to happen. Now p is 3a plus b over 4. We want that to equal a minus b over 2, and q, which is a plus b over 2, to equal a minus just a. So a is equal to a plus b over 2, which is good because now we can substitute that in here, and we have b over 2 equals a plus b over 2 minus 3a minus plus b over 4 equals 2a plus 2b minus 3a minus b over 4. So b equals b minus a over 2. So our substitution is going to be substitute x equals a plus b over 2 minus b minus a over 2 cos theta. Okay? Which makes dx equal to b minus a over 2 sine theta d theta. We've already worked out what the corresponding thetas are for these. So when x equals p, we found already that p2 equals pi over 3, because that's how we chose this integral in the first this substitution in the first place. Similarly, when x equals q, we know that theta is going to equal pi over 2. Fantastic. You'll notice here that this is where the b greater than a comes into play a bit. If b were equal to a, this would be 0, and actually, well, the substitution wouldn't work quite as well, basically. But actually, I think, I haven't done it, but this integral would be a lot easier. In fact, hang on. Yeah, I'm fairly sure that would just be a constant, but it would also be an imaginary one. Not good. Anyways, so here's our thing. P, Q, x, dx. So we can write that j equals pi over 3 pi over 2 of, now watch closely, b plus a over 2 minus b minus a over 2 cos theta minus a over b minus b plus a over 2 minus b minus a over 2 cos theta. Okay? To the half b minus a over 2 sine theta d theta. Now, this b minus a over here is lovely and a constant, so we can just take it out. We want one anyway in our endgame expression, so we can do it. Now, let's have a look at this big thing inside here. That cancels, because b plus a over 2 minus a is b minus a over 2. b minus a over 2 minus b minus a over 2 cos theta over b minus this lot is going to be b minus a over 2 plus b minus a over 2 cos theta times sine theta d theta, which equals b minus a over 2 of pi over 3 to pi over 2, and here it is, 1 minus cos theta over 1 plus cos theta to the, should be half there, half sine theta d theta. Now we could do this again, or we could realise this is all part of the same question. So we can justifiably write b minus a over 2 times I. For reference, I was what we called this thing here, which we proved went to this thing here, which is what we have now. We've already found an expression for that. It is this thing here. So we can shove it in. We can say this is equal to b minus a over 2 times 2 pi plus 3 root 3 minus 6. This is why at the time I made this weird reformation of this, because actually this means that we can now just simply write down our answer. This is b minus a pi plus 3 root 3 minus 6 over 12 as wired. Just a little bit of anatomy. What we did was we realised the kind of substitution we were going to do. We stuck some arbitrary constants in and found ones which we thought were going to work. They did work. It was lovely. It cancelled down to something we already knew, so we could just stick that in, and fazam, we have it. Whoa. That's an entire step 3 question. Pretty rad.